of the Lagrange spectrum of translation surface.
Thank you very much. So, as the title does not say, my talk will be mainly about triangles, as you will see, and Euclidean triangle, not exotic ones. And I will start first by recalling what is the Lagrange spectrum of, for rotations, and then explain two results that we have. So it's time to mention that it is a joint work with Michael Boscher-Nielsen, who is here. So it's, yeah, classical. So it has two flavors, depending if you are more a dynamical system person or a more Diophantine approximation person. So if you have alpha, number in 0, 1, which is not rational, you can look at the, so this is a number theoretic version. You can look, consider the supremum of the number C such that alpha minus P over Q is smaller than 1 over Q C square, no, CQ square for infinitely many PQ. So it's a measure of approximation. So let's call it L of alpha. And a more dynamical version is you consider the rotation by alpha from 0, 1 to itself. So just x go to x plus alpha. And L alpha can also be taken as being the limit, the inverse of the limit as n goes to infinity of n multiplied the, oops, it's R alpha x for any point x because it's an isometry, and minus 1. And so what is the Lagrange spectrum is the set of all numbers that you can get by looking at these quantities. So let me first say that, so what? Sorry? Yes, thank you very much. Yeah, you look at your nth, you're looking at the rate of recurrence of the map. And if you don't multiply by n, it makes no sense. This is a good quantity to multiply by. And so the Lagrange spectrum, let's call it L of 1. There will be generalization later with other numbers here. So L of 1 is the set of L alpha. And this is the Lagrange spectrum. And so we know, and the one important thing, oh, L alpha, like this. And L alpha, is for almost every alpha, actually, this Lagrange constant is just infinite. This is 0, and so when you take the inverse, is infinite. So equal, and when it is finite, it is equivalent of alpha to be bad, as in the talk of Yann Bugeaud. And bad means bounded partial quotients for the continued fraction expansion. So this is a small set of alphas for which it is interesting, but you get a very interesting set here. So let me make a picture of what we know about this Lagrange spectrum. So it starts at square root of, so it's picture of L alpha, of L1. It starts at square root of 5. There is a discrete sequence with the first accumulation point at 3. So first accumulation. Then you have some crazy structure in between. And after a crazy number, I do not want to write it, but which is an algebraic number of degree 2, which is around 4.528, you have everything. So a half line, So let me tell a bit more. So this is a the discrete spectrum is old and is related to binary quadratic forms, and it was studied by Markov. So this is for the discrete part. In the middle, we have very interesting work of Gugu Moreira around 2010 about the Hausdorff dimension, how the Hausdorff dimension increases as you look at when you go to the right. And it becomes 1 before being a half-line. This was one of the interesting results. So I have no the exact value is not known, I guess, but it becomes 1 before, which is something which is weird. And it becomes positive already at the very beginning, and it becomes 1 before starting to be full. And the half-line was proved in the 70s by Hall, who proved that there exists a half-line, and then the crazy value here was given by Freiman. OK, this is what we know. And the discrete spectrum here is always corresponds to values that are obtained for quadratic numbers, for which the continued fraction expansion is just periodic. This will play a role later on. And how do you prove such? All the results that are on the blackboard here are obtained because there is a very explicit formula for rotation for this quantity based on the continued fraction expansion. We have 2 generalizations of one thing, which is just the bottom, which is this point. So we will generalize this point to context. So the first one, theorem 1. So is that actually this bottom in this version of the definition is actually valid for any map that just preserves the Lebesgue measure on 0, 1. So if you have any t from 0, 1 to itself, measurable, preserving the Lebesgue measure, then for almost every the distance from t to the n x to x, this is smaller than 1 over square root of 5. And so this is an interesting phenomenon. And we do not know nothing more about what values can be achieved in this for any measurable map, just the fact that the worst constant is the square root of 5. And the second result is about interval exchange maps. So I need to define what is an interval exchange map. And IETs are somehow the simplest map that does preserve the Lebesgue measure, which are piecewise isometry. So you pick the segment 0, 1, you cut it into pieces. Let's say 4 for this example. And you reorder them according to a permutation that you choose at the beginning. So let's say D goes first, and then B, and then C, and then A. So, and these are translation. And if you have such a map, I will call it a 4IET, because there are 4 intervals with discontinuities. And there is another version of that theorem that does not look exactly at the recurrence rate, but how well the discontinuities approach each other. So the points where the map is discontinuous, be careful. Yeah, for example, this point, there is no discontinuity, but yeah, I marked it at the beginning. So I consider it in my set. So when I have an interval exchange transformation, I can define this finite set of points. I don't know. Here it's x1, 2, 3, 4, 5 singularities. And theorem 2 is that for T and a K interval exchange transformation, the limit as n goes to infinity. And we do not look at this quantity, but here we can put any xi and any xj. So it's n times the minimum of the distance from Tn of xi to xj for any ij. They might be the same, they might be different. And the result is that it is less than 1 over k minus 1 square root of 5. And this is, you cannot do better. And when it is this exact value, it corresponds in some sense to, it is extension, it is induced map of extension of the rotation by the golden mean. Yeah, I should have said this before. This square root of 5 corresponds to the alpha 1 plus square root of 5 over 2. And so the interval exchange that reach this, this bound are direct extension of this alpha. So today I will speak only about the theorem 2, but the flavor of the proof is based on the same argument. There is something more here, and the argument is based on a theorem about packing. And I'm going into that. But first, to make it more, to go to this more geometrical picture, I will need to reformulate the theorem in terms of translation surfaces. So my map was one-dimensional. I will make it as a flow on a surface, and it's two-dimensional, and triangles come from these surfaces. So a translation surface is nothing more than a suspension of an IET. So this is how we should think of it, so suspension of IET. So formally what it is, you pick a collection of triangles or polygons. I just say a construction in words, so it's almost a definition. So pick TI triangles, and we will glue them together to make a surface. And when we do the gluings, we want that the sides we glue are identified by a translation. Okay, and what you obtain when doing that is a surface. So it's a topological surface. It's not well defined at the vertices of the triangles. But everywhere else, you have more than a surface. You have a flat metric, which comes from the fact that the triangles were triangles in the plane, C, flat metric. And you have some, what happens around the vertices is that you have conical singularities. I will give example in a few moments. So there is no need of a formal definition for the rest of the talk. But I need to reformulate the theorem 2 in order to explain the method. So what is the first example is a torus. So how do you build a torus? yeah, something like that, where you identify opposite sides. So in my definition, I put triangles. So let's put triangles. You just cut that in two, and you have two triangles. And there will be an important parameter in the complexity. In the case of IETs, it was the number of intervals. And here, it will be the number of triangles. And they are very much related. So let's call D equal 1 in that case. It will be the number of triangles divided by 2. And as the total angle of triangle is pi, you can also recover this number as counting the total angle around the vertices. So let me give the case of, so these are suspension of IET, and why is that? If you consider a segment, I need to choose it well. Yeah. Oh, the color is not the good one. OK, I have a blue segment in my surface here. And in my translation surface, I can look at the flow, which consists just in go in the vertical direction. So in these surfaces, I have flow that I call the translation flow. Translation flow, which is just the flow that is induced from the structure of the triangle by the point V just go to V plus T times the vector 0, 1. So you just go up at speed T. So in this picture, if you start from the point which is on my segment, you just go straight, and then this is identified to this. So you go here, and then you go here. OK, and then you continue. So this is the flow. And if you look at the Poincaré map on the interval in blue that I just draw here, it's easy to see that what you obtain is an interval exchange with two intervals. And interval exchange with two intervals are just rotation. You are just making plus this quantity. If alpha is this quantity, you are just making plus alpha. So this is also a rotation. IET are particular case of rotation, and if you put k equal 2, you recover the fact that square root of 5 is the bottom here. All right, let's go to a less trivial example. You do, yeah, this is the preferred example of everybody. Up. Well, I cut into triangles because I put the triangles in the definition, and triangles are important for the counting. So here I have D equal 3. And if you do a first return map on a well-chosen transversal, you will get a 4 IET. And so what is the relation with my D, which is the number of triangles divided by 2, and the number of intervals is just D plus 1. So the number of intervals is just D plus 1, where D was my number of triangles divided by 2. And so this D plus 1, if you replace K by D plus 1, you see that it is 1 over D square root of 5. So D is a parameter that is more suited to put in the theorem. Why I'm talking about that? Because there is a way to express the theorem 2 just in more geometric terms. There are several reformulations. So you can use the translation flow to look whether your point approaches the other singularities. But I want another definition based on saddle connections. So in the case of torus, you know that the torus is just, you can define it also as the plane quotiented by lattice. So these are tori. And if you are here, and you look at what you see in a torus, you will see yourself in plenty of directions. And you can consider these as vectors. Each time you see yourself, you can consider it as a vectors and put it in the plane. And what you will see are exactly the primitive points of the lattice. So what are the primitive points? Is just the set of P V1 plus Q V2, where V1, V2 is any basis of lambda. So Z V1 plus Z V2 equal lambda. And PQ are relatively prime. So you need to choose a lattice first. Okay, it's almost a picture. And then primitive points is just that these points, you will not see it. If you are in the surface, you will not see it because this is blocked somehow by this. So this is not part of the primitive point, but these ones are. Okay, and you get a set of points in the surface. And so you get a discrete set in the plane, and from this we will get a generalization of this notion of the Lagrange constant. And this will make sense also for translation surface. So how you can measure this Lagrange constant is by looking at the quality of approximation somehow, by the area made by this segment. So yeah, segment has no area, so we had trouble with the definition, but we are measuring an area formed from a segment. And this is the area of the rectangle with horizontal and vertical sides that has this V as a diagonal. So let me define it. If I pick a vector V, I define its area, so its definition, as being the product of the two coordinates of V. So it's the real part in absolute value times the imaginary part. And with that, you can define what is the Lagrange constant of your torus. So let's say L of lambda, which is the limit as n goes to infinity of, no, not n, of area of V as the imaginary part of V goes to infinity, plus infinity. And V belongs to lambda or the primitive ones. Actually, it does not make any difference. But yeah, lambda prime is for primitive points. And not so hard proposition. Oh, and I need to scale it, sorry. In order, yeah, because if you scale the surface by 2, let's say the lambda is multiplied by 2, this constant will be also multiplied by 2. So in order to have a scaling which is independent of the area, I just divide by the covolume of lambda. And from this, you can show that the Lagrange of lambda is the same thing as the Lagrange constant of any induced rotation. Okay. And there is also another generalization, another way of expressing this constant, which is a bit more geometrical and which might be another motivation, is that on lambda you can act by 2x2 matrices, and in particular the diagonal ones. And another way, yeah, let me put everything in the same. It is also limit. Oh no, let me define S. So S of lambda is the lim inf as t goes to infinity And what you are measuring, you will measure something in GT lambda. So you modify your lattice, and you look at the shortest vector in your lattice. So this is total of GT lambda. So in that picture, this is this one. But after you apply this exponential matrix, this is another point which will come closer. And so you are measuring the rate, the smallest one that you see infinitely often. And this S is actually related here. And so proposition. You can also write this is, or perhaps I made, yes, I think I need a -1 here. So what is it? It's 2 over S squared. So why there is a 2 over S squared? Because if you have a short vector, imagine that it is the time it is the shortest is when it is at 45 degrees. And when it is at 45 degrees, its length is just square root of 2 times the square root of the area. So this is why you have this 2 and you have this square. So the fact that this equals the version with the area is easy. And I need to scale with the area as well. So yeah, there is a covolume here, sorry. This will not be important, but this is just to explain the connection that you have here. So it's not hard to see that this is equal to this. And it's not hard to see that this is the same definition as here. Because here you measure approximation from one singularity to another. Because the linear flow, if you follow the linear flow, you go here. So you are measuring some distance between x and some iterates. So these are the reformulations that will be convenient for me to work with. And so the question is how you get a discrete set in the plane from a translation surface. And these are the so-called saddle connections. So to a translation surface X, I can associate a set, a subset of the plane, which is discrete, which is a set of holonomies of saddle connections. And so what is a saddle connections? Here you have a surface that is obtained by gluing triangles. And you can consider translation in any direction. And for example, here is an example. And you have some segments in your surface that join two singularities or two vertices of your triangles. And such a thing is called a saddle connection. So and each time you have a saddle connection, you can associate a vector to it, which is its holonomy, and which is just the vector which corresponds to this translation in your translation surface. And so the set of holonomies of translation surface is just this set that you obtain by looking at all these vectors that join singularities. So there are plenty of them. It's everywhere dense in the surface. But it's discrete in the plane. So in the case of lattice, there is a property that all points are far apart from each other. And if you pick a random surface, that won't be the case. You will have points which will be very close together. But some of the properties of the lattice will be still true, like the fact that you have approximately r square point in a ball of radius r. So the number of points is comparable to the area of the thing you are looking at. So it's not known for all surfaces, but it's known for most surfaces at least. All right. And the definition I put here also makes sense for translation surfaces, right? Instead of looking v in lambda prime, so let me replace here by hex, you can just consider holonomy vectors, and you just consider the same definition. And the same proposition is true when you look at when you consider a translation surface, and you can also make the definition with the geodesic flow. So now I can state the theorem, which is the reformulation of the Lagrange spectrum. And actually, I will state a more precise version. You will see why. So it's part 3. So consider, let's define LD. I defined L1 as being the set of Lagrange value for any rotation. And you can consider LD to be the set of L of x for x being a translation surface. Made from 2D triangles. And let me emphasize that this is the same thing as L of t pi lambda of t, where t are IETs with d plus 1 intervals. All right. And what is the reformulized version? Is that the bottom is d square root of 5, but actually we prove that it is isolated in the whole spectrum, in the whole LD. So the bottom is d square root of 5, but this bottom point is also isolated, and we have a quantitative version. So LD. So there exists a universal C0 that I don't want to make it explicit. LD intersected with 0 d square root of 5 plus this constant over d is just the bottom, the value. So just to say that it is isolated. But we do not know, okay, this is one of the first things we know about this generalized Lagrange spectrum LD. There is, okay, you can say a lot of things based on the following fact. It's easy to show that if you multiplied L1 by the number d, it's included in LD. So how you show that? But you just pick a torus, and you just glue so you pick a torus for which the value, you know the value, and you just glue the torus to itself in the way you want. You choose a way to glue them. So for example, you glue it 3 times, and it's not hard to see that the set of holonomies will be exactly the set of holonomies of the original torus. So you will get exactly the same constant, except that I multiplied the area by 3, so there is a rescaling due to the area. So it's easy to prove that from translation surfaces. But if I gave you just the definition with IET, I'm not sure it's easy to prove such a thing. But yeah, it's just a simple lemma. And from that, of course, you can prove that you have a half line, because you just transport the half line in L1 to LD. But yeah, we have no idea where it starts in reality. All right. Now I can start with triangles. And why is there some packing involved? And the packing comes from these areas. So recall that the definition involved areas of holonomies of saddle connection. So I recall just the definition. It was the product of coordinates. And so if I want a surface, for which the value satisfies this, I want that all my area of saddle connections are big. So somehow you want to put triangles together in such a way that all the yeah, when you measure any segment with respect to this strange distance, they are far apart. So this is what we call packing. You have a distance and you want to put in some dense way points, but far apart. And so in order to do that, it's just elementary geometry. But when you use this distance instead of the usual distance. So let me state the main important lemma about these triangles. Oh, no, there is one important thing, is that there are bad triangles and good triangles in the story. So what is a bad triangle? So I will make picture in the surface. So each time you have a triangle in your surface, you can always embed it in a maximal square. And sometimes you will have picture like this, and sometimes you might have picture like this. And these are good triangles. And these are bad. So what is a good triangle? Is a triangle such that if you consider the maximal rectangle that encloses it, and rectangle is with horizontal and vertical side. The minimum rectangle that encloses it, the 3 points are on the boundaries, unlike this one. And in the very same way you have bad triangle and good triangles, you also have a bad segment and good segment. So a segment is good if you look at the rectangle that is around it, there is no saddle connection here. So these are just the diagonals of rectangles that you can embed in your surface. So these are what we call best approximation. And these are the very same thing as in the torus case. Oh, I erased my picture. But the best approximation, Pn, Qn, that you have when you consider continued fractions, you can define them in these terms. These correspond to vectors, such that when you make this rectangle, there are no other points in this rectangle. So this is a geometric generalization of best approximation. And it's not hard to see that if you have a good triangle, the 3 sides of the triangles are best approximation. And actually, the converse is true. It's a bit harder, but if you have one best approximation, it's a side of a good triangle. You can always make a triangle out of best approximation. And when you have a good triangle, you can even make a triangulation of the whole surface having this as one triangle. And the triangulation will be made only of good triangles. So these are important properties that I will write down. So there are, this is just a small lemma. So sides of good triangles are, let me call BA for best approximation. If gamma BA, I can build, there exists a delta a triangle, one of its side being gamma. A good triangle, sorry, good. Being gamma. And if I give you a good triangle, there exists a whole triangulation of the surface. So a decomposition of the surface into triangles, the very same way I define them by gluing triangles, having delta as one of each triangle. So I don't want to prove it, but the way you prove it is using what is called Delaunay triangulations. And it's not Delaunay with, perhaps you know the definition, but it's not Delaunay with respect to the L2 matrix, but with the L infinity matrix. And balls for L infinity matrix are squares with horizontal and vertical sides. And so this gives you triangles with this good property. So why do I care about good triangles? I care because I have nice formula that relates the area of the sides in the way it is defined there with the area of the triangle. So perhaps you know there is a formula in geometry that relates the length of the side and the perimeter with the area. So it's a sort of analog of this thing. So if delta is good, and if alpha, beta, gamma are area of the sides. Oh, and I forgot something. The situation is not completely symmetric. You see that one of the vertex is in a corner, and the other two are on the sides. And so one of the sides will play a special role compared to the two others. So when I write alpha, beta, gamma, the gamma will correspond always to the area of this one. You will see the formula is not symmetric in the three variables. So this is why I need to say that. And where is the formula? Then there is a formula which tells you that the area of your triangle is just a big square root of a quadratic form. And of course, it's symmetric in alpha and beta because you can reflect the picture. But you see there is a minus here and two pluses here. So this is why it's not symmetric. So very good. So the formula is not interesting in its own, but it allows you to prove many interesting things about what you need to do in order to do some dense packing. And so the main important thing is this corollary, which is one of the main ingredients in the proof of both of the theorem I stated at the beginning, actually. So it's not completely clear, perhaps, how you can extend this kind of strategy for measurable map. But yeah, if I have time, I will say a few words about it. So what is the corollary? Is that if delta is a good, then you can always so I call M the mean of the areas, and big M will be the max of the areas. And so the area of the triangle will always be in between square root of 5 over 2, the minimum, and square root of 5 over 2 times the maximum. So this is very easy to derive from here. But actually, you have better. But it's better, but only if delta is very close from being square root of 2, square root of 5 over 2 times the minimum. Moreover, the area of delta is not far from being this, and the not far from being this is square root of 2 times m, then you have a better formula, which is square root of m squared over 2, area of delta. And the same thing when you replace big M with small m on the other side. So, and this is wonderful, because if you know something on the area of the triangles you are studying, it will tell you something on the maximum area of the sides, which is something I want to quantify. So this is where we have something precious. So yeah, let me sketch the proof of the restated theorem that I already erased. So yeah, of proof of theorem 3. So let me start with the hypothesis. What I assume is that I have a translation surface X. And so in order to get rid of this D, I will consider that it has area D with area D. So what I want to prove is that if the areas of my sides are close from being 1 over square root of 5, then it is 1 over square root of 5. So hypothesis is the inf for V in this holonomy of X of area V is greater than 1 over square root of 5 minus some small epsilon. And what I want to prove is that actually this minimum is 1 over square root of 5 and not something else. But I need to choose epsilon appropriately. And so once, and perhaps you noticed that I put an inf instead of a liminf, but we can pass from liminf to inf because, as in the case of the rotations, you have density of the quadratic. So if you look only at Lagrange value for quadratic numbers in the case of rotations, it's dense in the Lagrange spectrum. So the analog here is that you can look only at the spectrum or surfaces for which the GT orbit, where GT is my diagonal matrix, is periodic. And when you have this periodic geodesic, the liminf is just an inf. So this is why. So this is a bit stronger than what I stated, but this is enough to do that. So the game is you know that, and you want to prove that actually this inf is 1 over square root of 5 and no more. So once you have that, you look at your. We look at the nice corollary, and what it tells you that if you know something on the minimum, that it is greater than something, then you know that all the triangles that you will be able to build in your surface will be relatively big. So this implies that for any good triangle, any good delta, area of delta is bigger than 1/2 minus constant times epsilon. And the constant does not depend on D yet. Yeah, perhaps you remember that I lose a D. There is a D involved, but you would see. So we know that. And now, here, I wrote that any triangle is contained in triangulation. And because you know that for all triangle, and the surface is made, if you do triangulation, there are 2D triangles. So you can reverse this inequality here. So you can reverse it using just the fact that each triangle is part of a triangulation. And you get that the area of the triangle is smaller than 1/2 plus some constant, but there is a D here, time epsilon. And from this upper bound, you can get an upper bound on the maximum. So, but only for best approximations, not for all vectors, of course. But you get that the maximum, the sup of V, a best approximation in X of area V, is smaller than 1 over square root of 5 plus a constant, which is not the same as here, D epsilon. And so what is important is that just from a hypothesis that I was far away from square root of 5, I know that for any good V, I am in between 1 over square root of 5 plus minus epsilon prime. This epsilon prime is roughly the size of D epsilon. And now, from such hypothesis, you want to prove that your surface is, that you actually exactly 1 over square root of 5. And the way you do this is using an induction, just finishing by citing Sébastien. You need some sort of unicity. So this tells you that you are very close at each, the whole GT. So what this tells you is that GTX is very close to a surface that looks like a cover of a torus, which is made as a rotation by a golden mean. And by using some induction procedure and unicity of this induction, you can prove that you are actually this surface and not another one. So it's, you can also get this, a non-quantitative version of it, just involving the hyperbolicity of the GT flow. But it's more interesting to have something quantitative. this is how you do it. And yeah, you lose, you see that you lose one D here, and in this argument, you lose another D. So this is why, perhaps you notice that there is a D square root of 5 plus C0 times D. So the gap we know between the bottom of the spectrum and the next value is something, there is a D square of difference, and there are two Ds that are lost in the proof. So I'm done with my talk. Thank you very much.
Thank you. So is there any question?